Today I will teach Introduction to Heat Transfer. Introduction to Heat Transfer will be covered major topics. See, look at here, the major topic covered here, the contents. First I will be teach thermodynamics. Next I will be what are the thermodynamics major applications in the thermodynamic laws and principle in heat transfer. Next I'll be definition of heat transfer, definition of thermodynamics, law of thermodynamics, Zeroth law of thermodynamics, first law of thermodynamics, and second law of thermodynamics, and then I'll be these three major law I have using, and one more law, that is the third law of thermodynamics. Then heat transfer, area covered under the discipline of heat transfer or application of heat transfer. Next will be modes of heat transfer. Next, modes of heat transfer. Uh, Conduction, there are three modes of heat transfer is there: conduction, convection, and radiation. Mechanism of heat transfer. What are the mechanism of heat transfer is correlated with the conduction and convection, then radiation. That is calling about mechanism of heat transfer. Next, the three mechanism of heat transfer is covered in conduction in Fourier law of heat conduction, and assumptions of Fourier law of heat conduction. And next, convection. Convection have depending on Newton's law of cooling. And next, radiation. Radiation is depending on Stephen Boltzmann constant. Next, I'll be moved from the thermodynamics. What is meaning by the thermodynamics? See, this thermodynamics word will be coming from the Greek language. Thermo means heat, dynamics means strength or power or energy. See, thermodynamics by means is the branch of engineering science. Thermodynamics is the science of energy transfer and its effect uh, on a physical property. See, uh, thermodynamics, especially from the heat energy is depending on so many applications in every day in life. Every day you have using from the heat energy. This heat energy, look here, what are the major applications of the thermodynamics laws and principles in heat transfer, especially from the basic thermodynamics and basic thermodynamics is the basic topic will be covered from the thermodynamics. In applied thermodynamics and heat transfer and refrigeration and air conditioning subject is the applications of basic thermodynamics. In applications of the thermodynamics laws and principles in heat transfer, first one, field of energy technology. Field of energy technology will be covered in first one will be covered in field of energy technology in IC engines and everyday life I have using for IC engines. Second one I have using for steam and nuclear power plant. Steam power plant to generate the electricity, and nuclear power plants also by using in the uranium to generating the electricity. Next, internal combustion engines. Internal combustion engines especially will be covered from the SI engines and CI engines. Next, I will move from the gas turbine. In gas turbines, you have using for generation of the power. And next, I'll be using for the air conditioning units. Air conditioning units by means AC and whatever your comfort life for the human beings, I am using in air conditioning units. Next, I will be go for the refrigeration units. Refrigeration units also you have VCRS, vapor compression refrigeration system, and vapor absorption refrigeration system, especially by using in see, next will be gas dynamic, jet propulsions. Next, I will go for the compressor, chemical process plants, direct energy conversion devices. These are all the device. These are all the major application part covered in the heat transfer application. See, uh, definition of heat transfer. Definition of heat transfer. Thermodynamics is the study of energy transfer either in the form of heat or work. The law of thermodynamics describes the relation between the matter and energy. It is based upon the experimental observation. Suppose I will be take example for IC engine. IC engine just uh, utilize the fuel, then get it energy. That is calling about definition of thermodynamics. That is calling about definition of thermodynamics, and that is the based on the experimental observations. Laws of thermodynamics. There are totally four laws of thermodynamics utilizing in Zeroth Law of Thermodynamics, first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. See, look at here, Zeroth Law of Thermodynamics. What can represent it here in Zeroth Law of Thermodynamics? When a body A in thermal equilibrium with a body B also separately with a body C, then B and C will be thermal equilibrium with each other. See here, this is the body A, this is the body B, and this is the body C. This is the body A, this is the body B, and this is the body C. Look at here, how can it will be transferred here? First you transfer the see here, body A it will be transferred to the body B, and body B it will be transferred to the body C. Again, body C it will be transferred to the body A. See, when A is in the thermal equilibrium with the body B, also separated with the body C, then B and C will be thermal equilibrium each other. This is calling about zeroth law of thermodynamics. Suppose example, you have dry in your car temperature in your environment. Suppose I drive the car from the office. You have car temperature and whatever surrounding temperature you have in 35-degree in car temperature and 30-degree in surrounding temperature. Then car temperature will be transferred to the in your surroundings or whatever in environment, and same car move from the in your house to in your office. Then whatever temperature is there in the car in the office, then it will be transferred. That is calling about body A to body B, body B to body C. It will be transferred. Then body B and C will be thermal equilibrium. This is calling about zeroth law of thermodynamics. Zeroth law of thermodynamics. Next, I will move from next will be moved from see here, body A to body B, body B to body C. This is also body A to B, it will be transferred thermal equilibrium. Again, body A to C will be transferred, that is also thermal equilibrium. Body B and C, zeroth law thermodynamics. Zeroth law thermodynamics. See here, temperature of the system A are equal to temperature of the system C. Similarly, if the system B is in the thermal equilibrium with the system C, then temperature of the system B equal to temperature of the system C. Now, above the relation, temperature of the system A equal to temperature of the system B. See here, next I will move from first law of thermodynamics. What can represent it here in the first law of thermodynamics? First law of thermodynamics, energy can either be created nor be destroyed, but can be converted from one form into another during any cyclic process of a closed system. See here, energy can either be created nor be destroyed, but can be converted into one form into another. This is work on it. That is first law of thermodynamics. Next, I will move from the Kelvin Planck statement. See it, what can represented here in Kelvin Planck statement. It is impossible to construct an engine which operates in a cycle, produces no effect other than the work output. exchanging the heat with a single thermal reservoir. See, it is impossible to construct an engine which operates in a cycle, produces no effect other than the work output, and exchange the heat with a single thermal reservoir. See, no heat engine can produce 100% work from the heat supplied or thermal efficiency of the heat engine cannot be equal to 100%. See here, say this is the T1, this is the main source, this is the heat engine. See, main source of fuel, once consuming the fuel in heat engine, then work can be that heat engine will move the piston upstate to downstate, then the energy will be conversion. Once energy will be converted in source to sink, then heat engine can get output from the work. That is the net work done. See, 100% consuming the fuel, there may be some 20 to 25% chances to loss, then get it the result from 80%. That is net work done. Net work done is equal to heat supply. See, this is the source and then sink. Once that fuel can consuming, then have uh, burning the fuel, then you have get smoke. See here, next, class statement of for refrigerator and heat pump. Especially, you know what is meaning by refrigerator. Refrigerator by means to maintain the temperature below the atmospheric level and below the your surrounding. Especially, so many cases we are using the refrigerator to maintain the temperature below the atmospheric level and whatever comfort in your human beings, that is calling about refrigerator. See, in heat pump, you have the reverse from the refrigerator. See, it is impossible to construct to a device that operates in a cycle and produces no effect other than transfer of heat from low temperature system to high temperature system. Low temperature system to high temperature system. This is calling about refrigerator. Next, look at here. See, in the refrigerator, what is meaning by refrigerator? Refrigerator is equal to work done by heat. See here in form, it is impossible to construct to a device that operates in a cycle to produces and produces no effect other than the transfer of heat from low temperature system to high temperature system. See, it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from low temperature system to high temperature system. That is calling about pump. See here, impossible system as per the class's statement. See, this is the main source and this is the sink. This is the source is equal to heat. I have a main source of heat supply. For example, engine main source of temperature in fuel. Once start to fuel burning, the temperature is T1 and sink, the temperature is T2 and heat pump. Q is equal to heat pump. Look at here, possible system as per the classic statement. This is the heat pump. This is the work done during the heat pump. Next, this is the source. See here, third law of thermodynamics, the value of entropy of a completely pure crystalline substance is zero at absolute zero temperature. This is calling about third law of thermodynamics. Next, heat transfer. Heat transfer is equal to the form of energy that can be transferred from one system to another as a result of temperature difference. As a result of temperature difference, uh, uh, the since that device deals with the determination of the rates of such energy transfer is called about heat transfer. Next, see, area covered under the discipline of heat transfer or application of heat transfer. See, major area covered under the discipline of heat transfer or application of heat transfer. First, design of thermal and nuclear power plants, including the heat engines, steam generators, condensers, and other heat exchanger equipment, catalytic converter, heat seats, for space vehicles, furnaces, internal combustion engines, refrigeration and air conditioning units, design of cooling system for electric motor generators and transformers, heating and cooling of fluids in chemical operation, construction of dam structures, heat transfer using improved insulation techniques, thermal control of space vehicles, thermal control of space vehicles, heat treatment of metals. See, these are all the major area covered under the discipline of heat transfer or application of heat transfer. See, design of thermal and nuclear power plants, including heat engines, steam generators, and condenser and heat exchanger equipment, catalytic converter, heat seals for space vehicles and furnaces. See, design of nuclear power plants. You know, one power plant to construct it to spend so much amount. Next, internal combustion engines, refrigeration and air conditioning units, design of cooling system for electric motor generators and transformers, heating and cooling of fluids in chemical operation, construction of dams, structures, heat transfer using improved insulation techniques, thermal control of space vehicles, and heat treatment of metals. See, modes of heat transfer. There are three modes of heat transfer: conduction, convection, and radiation. See here, conduction. Heat conduction is a mechanism of heat transfer from a region of high temperature to a region of low temperature within a medium or between the difference medium in direct physical contact. That is calling about conduction. See, heat conduction is a mechanism of heat transfer from a region of high temperature to region of low temperature within a medium or between the different medium in direct physical contact. Example for heating a rod. See, in front of fire you are standing, just to keep it in your hand in one rod, then continuously heat can transfer to the rod, then that it will be transferred to the in your hand. That will be mode of conduction. See, conduction, especially depending on Fourier law of heat transfer. See, the another definition is the conduction. Conduction is the transfer of heat from one part of the substance to another part of the same substance. See, conduction always transfer the heat in solid bodies. That is calling about one part of the substance to the another part of the same substance. See, from one substance to another substance in physical contact with it without appreciable displacement of molecules forming the substance. What is meaning by molecule forming the substance? Just I am get there are see here, this is the body A and this is the body B. This body A you have temperature from 50 degrees Celsius. This body body A you have a temperature from 50 degrees Celsius, and body B you have a temperature from body B, you have a temperature from 30 degrees Celsius. Once you have keep it in nearest to the place, or you have touch body A to body B, then body A heat will be transferred to the body B. Then body A you have 50 degrees Celsius is there. Body B you have in a equal to the ambient temperature is there. Ambient temperature by means having 25 degrees Celsius. Then gradually it will be transferred to the body A to body B. That is calling about mode of conduction. See, example of conduction, touching the stove being burned. What is touching the stove? We see, just keep it in stove and then have a cooker. Then whatever stove heat it will be transferred to the cooker. Then cooker inside you have a water is there. That water start to boil. See here, in you just touch the stove, then it will be transferred to the mode of conduction in your stove to hand. That is will be calling about mode of conduction. See here, you have stand is there here. Once the stand above you have keep in your stove, then continuously it will be transferred to the your hand. That is meaning by touching the stove being burned, that will be mode of conduction. See next, ice cooling down your hand. Just you have keep it in your hand in any ice. Okay, just keep it in your hand in any ice. Then ice start to melting. Then whatever temperature is there in your hand, then keep it in the ice. Then in your hand to ice, it will be transferred. That is also mode of conduction. Then ice continuously start to melting. That is calling about ice cooling down your hand. Next, a metal spoon becomes a art from the boiling water inside the pot. A metal spoon becomes a art. See, this is the cup of uh, decoctions. Just take the decoctions and you have keeps have mix some percentage of sugar and then have a metal spoon. Just have mixing this decoctions and the milk, then you have preparation for the tea or see this is also mode of conduction. This metal see here a metal spoon become a art from the boiling water inside the pot. See in your whatever this liquid to in your spoon it will be transferred. That is also mode of conduction. See this is there are three examples for conduction: touching a stove and being burned, uh, and next ice cooling down your hand, and next your metal spoon become a art from the boiling water inside the pot. These three have a mode of conduction, and one more you have a example. Um, um, you have morning pressing the your cloth. Just you take the cloth morning, just ironing. That is also mode of conduction. This is there are four examples for conduction. Next, I will go for convection. What is meaning by convection? Convection is the transfer of heat within a fluid by mixing one portion of the fluid to fluid with other. That is calling about convection. See, convection is the transfer of heat within a fluid by mixing one portion of the fluid with other. That is the mode of convection. See, convection is possible only in fluid medium, is directly linked with the transport of medium itself. The effectiveness of heat transfer by convection depends on largely upon mixing portion of the fluid. This is the mode of convection. See, example of convection, boiling water. See this boiling water, the heat passes from the burner into the pot. See, the heat passes from the burner into pot, heating the water at the bottom. See, this bottom continuously heat is supplied, then water gets start to boil. Density of water will be decreases, then whatever water density will be decreases, then that decreasing water can move the upward and upward water comes to the downward, then continues to start to boil. That is calling about then this hot water rises and pulls the water move down to replace it, causing a circular motion. This is example of convections. See here, this is this burner continuously it will be supplied to the cooker. Then cooker inside water is there. That water, that cooker to water it continuously transfer. Then water density will be reduces. Once water density will be reduces, continuously boil the water in down state to up state. Then continuously start to boiling. That is the boiling water. Next, radiation. Radiation is the transfer of heat through the space. See, radiation is the transfer of heat through the space. It is the heat transfer by the electromagnetic photons. It does not need propagating medium. The energy transferred by the radiation but moves the speed of light. Speed of light. See, this is three law. See, example of radiation. Uh, see, radiation is the transfer of heat through the space. See, in conduction and convection, you have a medium, but radiation there is no medium. Okay, just you have sunlight is there and earth is there. In sunlight to earth, the transfer of heat, then it will be transferred. That is calling about radiation is the transfer of heat to the space. It is Heat transferred by electromagnetic waves or photons, it does not need a propagating medium. The energy transferred by the radiation moves at the speed light. That is calling about radiation is the transfer of heat through space. Example, sun rays. Sun rays continuously focused on in your ground. That is calling about radiation of heat transfer. Next, radiation. For example, if I place the object under the direction of sunbeams, I will note in a little while that the object will be heated. That exchange heat between sun to in your object. That is calling about radiation. See, for example, especially in your environment or surroundings, there are so many objects and so many things there. Just in sun continuously radiated to the earth, then that all the object can heat it. This is calling about mode of radiation. Look at here, your car will be standing in outside of the park, outside in your office park, just to have sunbeams. These sunbeams continuously supply to the in your car, the heat transfer from the sun to earth, example of radiation, it is transferred but it does not warm the medium through which it passes. Radiant heat will warm interior and exterior of the vehicle that is parked in the sun. That is calling about radiation. Next, mechanism of heat transfer. Mechanism of heat transfer, first one will be conduction, another one will be convection, and will be radiation. See, totally there are this is the conduction. This is the conduction. See what is calling about mechanism of heat transfer. Mechanism of heat transfer is calling about combined mode of heat transfer. What is meaning by combined mode of heat transfer? Combined mode of heat transfer by means to combine. See combined mode of heat transfer. Combined mode of heat transfer means combined mode of heat transfer. Combined mode of heat transfer by means see combined mode of heat transfer by means of see look at here. This is the stove. Stove continuously supplied to the heat from the your cooker. Once that heat will be transferred mode of conduction. See mode of conduction. See here physically touch with the stove hand, that will be mode of conduction. Then you'll be looking here inside the water will be convection, and standing in front of you, that will be mode of radiation. That is the mechanism. That mechanism of heat transfer. Mechanism of heat transfer. Next, I'll be move from heat transfer by conduction. See, there are three laws there in heat transfer. One will be mode of conduction. Mode of conduction, the rate of flow of heat through a simple and homogeneous solid directly proportional to the area of the section, right angle to the direction of heat flow. Change of temperature with respect to length of the path of heat flow. See what is meaning by the rate of flow of heat through a simple and homogeneous solid. See here, Q equals minus Ka. Q equals minus Ka into dt by dx, dt by dx, dt by dx. See here, what is meaning by minus Ka into dt by dx? See, Q equals to heat transfer. Q will be represented heat transfer, heat transfer in watt, heat transfer in watt. K is equal to thermal conductivity. Thermal conductivity. Thermal conductivity E is equal to thermal conductivity. And next, dt by dx. dt is equal to change in temperature. Change in temperature. And dx is equal to change in length. Change in length. Change in length. Change in length in meter. In meter. Change in. See here, the negative sign will be represented here. This will be decreasing the temperature. Always material it will be transferred, will be reduces. Always it will be transferred to the in your particular object or particular material to your surroundings. That will be negative sign. See here, Q is equal to minus Ka into dt by dx. Q is equal to heat transfer in watt. K is equal to thermal conductivity. dt is equal to change in temperature, and L is equal to change in length. Just I will be writing here in the diagram. Just draw the diagrams. See here. This is the T1 temperature. T1 temperature. Next, T2 temperature. T2 temperature. And this is the L. L. This is the heat Fourier law of heat conduction. The rate of flow heat through a simple homogeneous solid is directly proportional to the area of the section, right angle to the direction of heat flow. To change the temperature with respect to the length of the path heat flow. See here, this is Fourier law of heat conduction. Fourier law of heat conduction, Q is equal to minus Ka into dt by dx. This is Fourier law of heat conduction. Then next I'll move from convection. Next I will move from convection. See, assumptions of Fourier law of heat conduction. Conduction of heat takes place under the steady state conditions. Heat flow is unidirectional. The temperature gradient is constant, and the temperature profile is linear. There is no internal heat generation. The bonding surface are isothermal in character. The material is homogeneous and isotropic. Value of thermal conductivity is constant in all the directions. This is the assumptions of Fourier law of heat conduction. See, conduction of heat takes place under steady state conditions. The heat flow is unidirectional. The temperature gradient is constant, and the temperature profile is linear. There is no internal heat generation. The bonding surface are isothermal in character. The material is homogeneous and isentropic. The value of thermal conductivity is constant all the directions. This is assumptions of Fourier law of heat conduction. See, see here, steady state condition, temperature within the system does not change with the time. Unsteady state conditions, the temperature within the system vary with time. These are the assumptions of temperature. Thermal conductivity of materials. Thermal conductivity of materials, the amount of energy conducted through a body of unit area and unit thickness in unit time when difference in temperature. See the amount of energy conducted through a body of unit area, unit thickness in unit time when the difference in temperature between the phases causing heat flow is unit temperature difference. That is calling about thermal conductivity. See here in thermal conductivity, uh, the watt per meter Kelvin. See watt per meter. The units of thermal conductivity, watt per meter Kelvin. Next, I will move from. See, there are different materials, thermal conductivity of materials. See here, especially gold have a more thermal conductivity, but in application point of view, in gold have not using serial number materials. In materials, first one will be silver. Silver is equal to 410 watt per meter Kelvin. Copper 385 watt per meter Kelvin. See, afterwards, aluminum you have a 225 meter Kelvin. Cast iron 55 to 65 watt per meter Kelvin. Steel 20 to 45 watt per meter Kelvin. Concrete 1.20 watt per meter Kelvin. Glass 0.75 watt per meter Kelvin. Asbestos sheets 0.17 watt per meter Kelvin. Ash 0.12 watt per meter Kelvin. See here, ash and cork felt is 0.05 to 0.10, sawdust 0.07, glass wool 0.03, water 0.55 to 0.7, Saran 0.0083. This is the thermal conductivity of the material. Thermal conductivity depends essentially upon the following factors. First one will be material structure, density of the material, moisture content, pressure and temperature conditions. See, thermal conductivity, you have know how much amount of heat can transfer. That is calling about thermal conductivity. You have material structure. For example, in material structure, in solid body and liquid body. Solid body, the molecules will be bonding in very closely. That is calling about material structure. And next, you have in the liquid state and gas state. And depending upon the material structure, density of the material also depends on copper, aluminum, and stainless steel, depending upon the material and different density, moisture contents, and pressure and temperature operating conditions. This is the thermal conductivity depends essentially upon the following factors.